Hello and welcome to another episode of the book club, Computer Organization and Design. I was rather underwhelmed, or I guess you could say disappointed, with the last section, 2.7. I felt the exercises were lacking, and the fact that they covered loops and or a while loop and an if-else before introducing the unconditional jump, the unconditional branch, or jump. I didn't really like how they chose to structure things in that regard with the examples they gave. I felt they should have covered jump instructions first. So I think I'd say that was my least favorite chapter so far, or section at least. But I'd still say this is an amazing book. Don't get the wrong impression here. I think this is definitely the book to go to for this stuff. And Patterson and Hennessy are quite influential figures. This and the computer architecture book are, kind of the gold standard. And they recently got the Turing Award for their work. That was just earlier this year, or maybe last year, I don't remember. I think it was early this year that they were awarded the Turing Award. And Patterson, I don't know about Hennessy, but I know Patterson was very involved in the early development of the RISC architecture concept, and is still involved with it, with RISC-V and everything. He's like on the board of advisors or something for Sci-5, for example. And yeah, like I say, I don't know about Hennessy, but they've they're pretty smart guys, pretty influential figures. Nothing but respect for them. And as I go through this book, of course I critique it and give my opinions, but I just want to stress that I'm not hating on them, and I'm not hating on the book, even though I read it critically. I think it's good to read books critically, even if as long as you have an appropriate level of kind of reverence and respect for the authors and the work that they've done. I was reading, or not really reading, but looking through a book that a friend of mine said he was reading, which was Lang's Basic Mathematics. I don't know how you pronounce his first name, Serge or Serge, something like that. But Lang is a very influential figure in the world of mathematics. He contributed a lot, and he wrote very prolifically. And so this particular book is on kind of just the basics of mathematics, as the name suggests. And so my friend was reading that, and I figured I'd take a look at it. So I was just skimming through it and was critiquing it as well. And we had an interesting discussion about that, of reading critically. And so I thought I'd mention that here too. And then kind of funnily enough, as I was flipping through that book, just skimming through it, it gets to a section where Lang discusses in the book kind of how to approach reading, and how a book like that, you can start in the middle of the book, you can skim through it, you can skip over things that aren't interesting to you and go back as you need things, and so on and so forth. And the different approaches to reading and studying, and he was discussing that, and in closing of that little chapter of that book, he mentions that, you know, any book, and I mentioned this too before even reading that section, talking to my friend about reading critically, that, you know, any book, no matter how, you know, great the authors are and how great the book is, any book will have its issues and things that can be critiqued about it. And that doesn't necessarily mean that the work is bad or that it takes away from the work. And it was just funny to see at the closing of that chapter in Lang's book, he mentions this, and he says kind of like, he has this kind of, I guess, closing paragraph where he's sort of calling out the haters. And I take it he's had some critiques of his books, and he's not so much a fan of receiving people's critiques or something, because he says that, you know, if you find things that you think could be improved, or are, you know, not what you would agree with, or whatever, stuff of that nature in his book, then, you know, you can correct it yourself or go write your own book. Like he says in the text, like, you know, go write your own book if you don't like it, something like that. And I thought that was very funny, so I thought I'd mention that here since it's sort of related. But anyway, let's get into 2.8 here. This one is supporting procedures in computer hardware. And right off the bat here, I'll say in the margin, it says procedure is a stored subroutine that performs a specific task based on the parameters with which it is provided. All right. A procedure or function is, oh, and you know, before I even start reading, that's one thing I want to say too, is a bit of kind of unfortunate, what would the term be? I guess parlance, or you know, lingo that's kind of circulated thanks to, I guess I don't know what languages kind of are responsible at the root of it, but like C, for example, we call procedures functions, and that's kind of unfortunate terminology because, you know, it kind of comes from the mathematical tradition of mathematical functions, but a procedure is very different from a mathematical function. And it's kind of bad terminology because mathematical functions do have their relationship to computer programming, in that on the theoretical side, Alonzo Church did the lambda calculus, which is computing, or I should say, you know, doing mathematics with nothing but anonymous functions, basically mathematical functions. And it turns out that that notion is actually Turing complete. It's equivalent to Turing's work with, you know, Turing machines, and capable of arbitrary computation in the same way that a Turing machine is. And so that is a, you know, a basis that led to kind of the branch of functional programming. And additionally, extending it with typing leads to type theory, which is very important to both mathematics and computer science, and things like doing automated you know, proofs of things and showing the correctness of a program. And interestingly, it kind of turns out that on some level, proofs and programs are kind of the same thing, and basically the thing you're proving is equivalent to like the type of the program, or something like that. Don't quote me on that, but there are relationships there. And then that kind of gets into the whole interesting thing of, you know, trying to prove the correctness of your program, well, it gets to a point where how do you know your proof is correct? What if you have bugs in your proof? And so I think there's kind of limited application of that, of using formal proofs to show the correctness of a program. It has its application, but at the same time, as your program grows, so too does your proofs of your program's correctness. And because proofs and programs are kind of, in a sense, isomorphic, you run into this problem where your proofs are just a convoluted form of program, and you have all the issues of writing a program with writing your proofs. So if you're trying to use your proofs to help you with your programming, to show the correctness of your program, well, what are you doing to show the correctness of your proofs, right? It's kind of a chicken and egg situation that I find kind of interesting, but I digress. What I was talking about is that functions in the mathematical sense, they do have their applications in computer science, and that's kind of what functional programming is all about. And so these concept of pure functions which don't have side effects, and they take one input and produce one output, everything's immutable. It's what you call pure functional programming. And these pure functions, as you will, are functions in like the mathematical sense. And that's very different from what a procedure is in computer programming, where the taking one argument thing isn't strictly an issue, because for mathematical functions, what you can do is called currying, where you have a function that returns a function that takes the next argument. So you can have an arbitrary number of arguments, basically. I won't get into the details of that, but in a C program, when you're working with functions, a procedure, it can take a number of arguments. It modifies state. The arguments are not immutable. You can do all kinds of crazy side effects. It's not equivalent to the mathematical sense of the term at all. And really, procedure is a better term for what we call in C a function. And that's one bit of terminology that I want to kind of correct in the hula language that I'm going to be doing on the series. We're not going to be calling procedures functions, we'll be calling them procedures. And that's the same thing that Jonathan Blow is doing with his language, I believe, as well. And I just want to stress that kind of there's some incorrect terminology in the world of programming today, where oftentimes when someone says function, they really mean procedure. And you should be aware of the kind of the difference there between a procedure, a series of instructions that can do any kind of state modification, and a mathematically pure kind of function. So that's just something that you should definitely be aware of, that there's a difference there. So just keep that in mind. But anyway, it says here, a procedure or function is one tool programmers use to structure programs, both to make them easier to understand and to allow code to be reused. Procedures allow the programmer to concentrate on just one portion of the task at a time. Parameters act as an interface between the procedure and the rest of the program. And data, since they can pass values and return results. We describe the equivalent to procedures in Java in section 2.15, but Java needs everything from a computer that C needs. Okay, I'm not sure what they're trying to say there. I guess they're just saying that Java is kind of funny in that it's very much an object-oriented programming language, and so you don't have free functions. Everything needs to be in a class, and so you have member functions, and but they're saying that basically you don't need to worry about those details. That you know, it's the concept carries over between languages. This is a very general concept. I think that's the point they're trying to get across here. Procedures are one way to implement abstraction in software. And so that's, remember, one of the big ideas of this book is abstraction. And, you know, this is a concept where, used appropriately, is actually a useful form of abstraction. Whereas, you know, I've ranted on this series in the past about how too much abstraction, or, you know, the incorrect use of abstraction can be, I guess, a boon to software development. This is an example where, used correctly, it's actually a very good tool. So basically, the way procedures are useful is that as you write a program, and this is what Casey Muratori teaches as kind of compression-oriented programming, he calls it, or something like that, the concept. And it really, almost in my mind, it's such a simple thing, it doesn't need, it shouldn't at least need a name. It shouldn't, like, it should just be the obvious thing, but sadly that's not the case. But then again, you know, it's maybe one of those things where it's something you can take for granted when you know it, but it's maybe not so much of an obvious idea until, you know, someone smart comes along and it has that little spark of ingenuity. And I think that maybe is the case here, that it's something that's obvious in hindsight, but maybe not so obvious without that experience or you know, hindsight to benefit you. But essentially, the way you should write a program is just, you know, you literally just do it sequentially. You just write out the code all straight line. And what naturally happens when you do that is that patterns will start to appear where the same sequence of code kind of repeats itself. The same structure appears again and again in your program. And you can lift that out into its own procedure, and so then you can get good code reuse that way. Sadly, some schools of thought today teach a different approach where, you know, very, very simple things like everything should be broken up into a function, and they teach you should just have like a straight you know, sequence of like function calls and no control flow in the, you know, the main program you're writing. Everything should be broken up into its own little function, and that's a terrible idea, right? That's a bad example of using procedures for abstraction. I would say pretty strongly that I disagree with that approach, but like I say, if you just naturally write out the code, the structure of the program will kind of reveal itself to you, and it will become apparent to you. The program will reveal to you what should be a procedure, basically. And you know, this kind of thing can have actual real world implications in terms of performance too, because one thing that tends to be rather complicated is inlining, of how a compiler will decide to inline something. And that's interesting if you think about it, because there's kind of a cost-benefit analysis there that goes on, where sometimes it is worthwhile to inline a procedure and sometimes it is not worthwhile to inline, and it's better performance-wise to actually keep it a procedure. And so it follows from that, without digging any further into that, just if you take that for granted, it follows directly from that procedures can be beneficial in some cases to performance, right? Whereas sometimes inlining can be more beneficial, which is, essentially it's where you just take the body of the function and you paste it into the code, so to speak. You're just eliminating the abstraction there. But inlining specifically is more of an optimization where you have that abstraction in your code, but the compiler decides to kind of eliminate that abstraction when it actually compiles down in a certain location. It kind of strips away that abstraction because it can be better for performance. But like I say, it doesn't always choose to inline, and so you should be able to see just from that clearly there can be some benefit there to your program's performance of having procedures as well. The other thing to say about procedures is that, well, I just lost my train of thoughts, but if I think of what I was going to say, I'll go back to that. But yeah, oh, I remember. The other thing about procedures is that not only is it kind of useful of when you have this repeated structure happening again and again in your program, but they're also incredibly important for separating backend and front end of your program, which is how you, I'd say, in my opinion, it's the best way to kind of structure a program, which is essentially you break your program up into front end and back end, and then you can swap out backends. And so you have backends for each platform that you want to target, and so you can have code that is specific to a certain platform contained within each, backend, basically. And kind of the alternative to that is to try to either write everything so that it's cross-platform, which at some level you need to think about the details at some level. Even if you're not doing it, someone else is doing it in what you're depending on. At some level you do need backends eventually, but you can try to write things to be very cross-platform, but what you'll find is that, and I've talked about this before, that really cross-platform, you can't really have something that's truly cross-platform. It's kind of been a failed experiment where you just head over to a website and just like look at these icons right here, because I think it's just because I have my font is set larger than usual, and the icons up here are like bleeding into the text. They're like not formatted well, because the web designer of this Twitter website here didn't take into account that when they were structuring how the website will be styled, didn't take into account that someone might have a configuration such as mine, and the result is this ugly bar up here. And you see that everywhere. It's kind of a failed experiment of people have tried to make things that are very abstract in general, and you can run this everywhere. A website works everywhere, right? But I see all around me things where things are not laid out well, things do not work on various platforms, so on and so forth. The whole kind of big idea of having everything be cross-platform hasn't panned out, in my opinion. I think there will be layout issues, there will be compatibility issues, there will be all kinds of things, and that's just an unavoidable fact of life. And if you want something like this to be handled properly, you need to actually, you know, as the designer, recognize that someone might have a configuration like this, where they have a font of a certain size, you know, a window of a certain size, whatever the issue is, you know, and special case for it. You need to kind of factor that into your design decision, and essentially that's platform dependent behavior in its own way, in that in this case we're talking about the font size as being kind of the platform dependent feature here. But, you know, it can also be something like the size of the display. Like on a mobile phone, you have many, you know, tons of different phones, and they all have different size displays, and you know, how things are laid out is going to depend on the size of that display. And it's the same kind of issue here with, you know, the font size that the user chooses to use, and those sorts of decisions. You need to think about all the possible combinations and have a good layout for every possible layout. And if you aren't properly thinking of all the possibilities, you're going to end up with some ugly corner cases that users are going to run into. And that's why I feel pretty strongly that the concept of cross-platform, portability is a giant failed experiment. It hasn't worked, and essentially there's a sweet spot where you can have a lot of your program be cross-platform, so to speak. You can have the majority of your program's logic be cross-platform, but you need to build it on a backend, and each backend needs to do that special casing to handle those sorts of issues. And so that's what I'm kind of stressing here, that with procedures, this is one of the things you can do, is the way you can structure your program. And I can show this off. Let me see here. So I work on pcalc, of course, and now let me just move some of the code over here. Okay, what all do we have open here? So if I go to, like, at this level here, I have actual assembly code for Linux x86-64 to start up the, call the main and set up the arguments to the main function and stuff like that. This is just pure assembly. And then from there, we have stuff that's, interfacing directly with the Linux platform. And, this is all very platform dependent code, but this is contained within a backend. And what I've done is I've just abstracted over, here are the things that I need to interface with directly with, Linux. Like if I need to do an open system call or a read system call, then I've, written a little wrapper that will do that call in assembly for me, and then I can go over to backend X11. And so, this is my backend, and you can see the main function here that gets called from the assembly code that I just showed you. What it's doing is it's just calling the front end main. So this is backend main, but it's calling front end main. And so, if you look through the backend, what I've done is I've abstracted the functionality that I need is essentially just abstracted away into a manner such that I can call this stuff from the front end, and for a different platform, the implementation of these procedures will be very different, right? But the point is, you make an API separation where you have front end and back end, and the front end calls the back end procedures, and the back end procedures are used to do platform specific work, right? And so you just contain all the stuff that you're not going to try to solve in a cross-platform way. You say, you know, some of this stuff needs to be done in a platform-dependent way. We're just going to contain the parts that need to be done in a platform-dependent way into a, you know, a backend layer. So like my create window backend procedure here is doing all kinds of crazy stuff to talk directly to X11, right? It does tons of stuff, but that's because it's, you know, it's talking directly to the X11 server and setting things up for that. And you know, if you look through here, a lot of this backend's not done, but you know, I just abstract all kinds of stuff, like you know, say I need to clear, I need to draw some black text, I need to draw reverse video text, gray text, I need to render rectangles, the cursor, I need to display the window, you know, the stuff to the window, I need beeps, because I do that as well. The stuff for waiting for events, you know, all this kind of stuff, I just say, you know, that's the level where I don't want to, you know, try to make this cross-platform anymore. I just want the platform-specific code to do those things for me, right? I just decided that's where I'm going to make the split, right? And so then if you go to another backend, like here's the XCB backend, you can see it has its own way of creating a window. And again, this is talking to an X server, but this time we're using a library to help us out. And we can see I have the wait for events here. It handles that sort of thing. We have the beeping implemented here. We have, you know, render clear, and you can see this is doing platform specific stuff. It's, you know, calling XCB procedures. Same with rendering various things, right? This is all platform specific stuff. But then the reason you do it this way is because you can go to my front end where I have the rendering code, and you see it's just, you know, it's this code here is totally cross-platform in that it just calls the backend procedures, and so it you know, it doesn't need to do anything that's specific to a particular platform. That's kind of the big idea of how to structure a program in a clean way. And you know, if you want to learn as a programmer how to make that separation in a, you know, in a good way, there are great code bases you can look at. Look at Handmade Hero. You can watch his series and see wonderful examples of that. You can see examples of that if you look at Per Vansen's code base for the implementation of Ion and some of his other stuff that he does from Bitwise. You can look at one that I really enjoyed was Serge's Milton code base. Of course, I worked with that because I needed to port it to Linux and modify it in order to use Milton here on the series, which I use like every day. In order to have this for the show, I needed to, you know, go in and actually monkey around with that code. And I was very impressed with his code base. I think it's a great example of how you can structure a program in a very clean way, separating front end and back end. and that's a great one to look at if you want to learn this stuff. The pcalc codebase will be available when it's done, but you can see, you can kind of see it from watching the pcalc series that I do. You can see the code a lot, and again, if you go to, just one more example here, if you go to here's the front-end main, and you can see it's pretty clean. It just gets the context from doing an init of the backend. So any backend specific stuff that needs to get initialized happens here. You set up a window with create window. You have event and state structures, and then you just loop while the program hasn't quit. You wait for events because this is just a calculator, so waiting for events is a fine strategy there, unless I want to add some kind of fancy animations at some point. So that might become a little bit more complicated, but right now there's no plans for that. It's not meant to be a pretty program. It's meant to be a functional program. Just meant to get work done, right? And so then we call update and we call render, and there's a garbage collect. It's not actually a garbage collector. It's just it just clears out the region of its region allocator. So but yeah, it's a pretty simple structure here, and it's all this is all cross-platform. There's nothing platform specific happening in here, and same with update and same with render. This stuff is all all the important meat of the program, the logic of the program and everything is all written in such a way that it doesn't depend on anything platform specific. So it's cross-platform, but then when you do need to do something that's depends on the backend, depends on the platform, you put that in the backend, right? So like creating a window obviously depends on the platform. So to do that, you can see there's BE underscore, because this is a backend specific thing, and it's up to the backend to implement this, right? That's the way that structuring a good way to structure a program to kind of separate the front end and the back end. That's a very important idea in programming, and I think it's kind of like one of the big ideas of how to successfully write a good program. And in order to do that, kind of the whole thing there, that depends on procedures, right? The reason I'm talking about this right now is because this is entirely dependent on the concept of a procedure, right? Because you're making a split in the code base, like an API split, where the front end is gonna, if it needs to do something platform specific, it needs to go through a backend call. And so that backend call is a procedure, right? So you need to make procedures that encapsulate functionality that is platform specific, right? And that ends up being your interface to the backend. And so each backend needs to implement that interface. And that's a way that you use procedures to do a kind of abstraction. It abstracts away the platform specific details because you're defining an interface, and then each backend is responsible for implementing that interface to provide the platform specific details. And so the abstraction that you're doing there is that the front end doesn't need to care about the platform specific details, right? The front end doesn't have anything in it that depends on a particular platform. When it needs to do something that depends on a particular platform, it has to go through the backend. That stuff has been abstracted away into backends, right? That's the big idea. And that's one of the important things that procedures give you. Another important thing that procedures give you is, like, if you watch Handmade Hero, one of the things you can do is hot code reloading. I know Deluxe has some pretty neat stuff in that regard too, in his game that he's working on, the Melodist. So if you watch his devlogs, you'll see some very cool stuff that he's doing there. And again, the way that sort of thing is done is you have procedures, and you compile down to a shared object, and then you're dynamically loading that at runtime. And so the key concept there is, again, procedures, because you're using procedures to define an interface, and then you're just kind of wrapping that up into a shared object that you can dynamically load and unload at runtime. But procedures are the key concept again there. The fact that you can have shared objects that can be loaded and unloaded at runtime is just a kind of a neat system level concept that follows from this concept of having procedures, because procedures define an interface. And so if you have an interface like the signature of a procedure that you're going to call, then you can say, well, why do we even need that compiled into the program? We can have that as a separate object that the program loads in. And if the program knows the signature of the procedure it needs to call, with a certain amount of infrastructure in place from the operating system, you can wire things up so that the program can call things from the shared object at runtime. And that gets misused a lot, in my opinion. I think people write libraries, and then you have libraries that depend on libraries that depend on libraries, and you get this dependency hell. And I think that's a big problem in today's software. People depend on way too many things for things that they really don't need a library to be doing for them. And that's kind of what pcalc is all about, is I'm writing a backend from scratch that literally depends on nothing. If it needs, it'll go all the way down to assembly when it needs to do platform specific things, as I just showed you, right, in the X11 backend. So I feel like it's very beneficial to, even if you're not going to write code that way, trying it to get that experience. And from an educational point of view, I think it's very beneficial. But I think that software should really be written much closer to the way pcalc is being written than the way that most modern software is written, where you depend very heavily on libraries. But my point is that dynamic libraries, shared objects, can be useful in practice, because rather than using them for something like libraries, dependencies like that, you can use it to do some very interesting things with like hot swapping, hot reloading code for development purposes. And forcoder is another great example of that kind of feature being used in a good way, where Alan Webster uses it so that what you do is he has his core program of forcoder be his own code base, which is closed source and proprietary and whatever, but then he distributes basically some stuff that you can modify, and so you can write your own customizations for forcoder. And again, the way this works, the big idea is there's a layer of abstraction there by procedures, where you can call a procedure that Alan has defined for you, that the core of forcoder has built into it. But in your code, you can call that API to do useful things, and so you can customize forcoder in this way. And then what happens is it gets built into a shared object, and your custom code is in the shared object, and forcoder goes and it loads this custom code at runtime and links up with it, so that you can customize forcoder in that way. And that's a great example of shared objects being used in a useful, in a good way. But all of this kind of stuff, these examples I'm giving you of Handmade Hero, the Melodist, Forecoder, using dynamic objects, shared objects, dynamic libraries in a useful way, and stuff like Milton and Handmade Hero and Bitwise and pcalc, all these things, abstracting front end and back end in useful ways. These are all examples of good uses of abstraction in software, and they all are based on the concept of procedures. So procedures are very, very much a great tool for programmers, and that kind of abstraction is actually extremely important and useful. So, used correctly, abstraction is very much a big idea of computer science and is very important. But the thing is, there's a nuance between good abstraction and bad abstraction, and most software today doesn't make the right kind of trade-offs. And if you surround yourself with kind of the culture of handmade-network, and watch stuff like Handmade Hero and Bitwise, and look at like the Milton code base, look at the code I'm writing, look at what Delix is doing, and all this sort of thing. There are many examples in this kind of space of programming where you can see great examples of how to do it right? And that's kind of, we're living in I feel like we're really living in an amazing time, because people like Per Vonsen and Casey Muratori and Jonathan Blow and, Sean Barrett some in the past, and Sean McGrath, and many very experienced programmers are, programming live on Twitch. They're putting their code out there. They're doing projects where you can study from it. And so, you don't need to be in such a lucky situation that you're working under a very experienced professional programmer in order to get this kind of experience like they needed to do in their lifetime. When they started programming, to get that kind of experience, they had to get it the hard way and maybe be lucky to be in the right place at the right time. And I believe Casey has said that if it wasn't for like Jeff Roberts being able to learn from him, and maybe other people, I don't remember, but he was very lucky that he was able to work with amazing programmers, and because of that, he learned how to develop software in a good way. And not many people have that kind of experience where you get to work with those sorts of people that really know what they're doing, right? And you're not learning this stuff in school, sadly. Schools aren't teaching this stuff. And so we're really living in kind of the great time, the greatest time to be alive as a programmer, I think, because we're in a day and age where experienced programmers like Casey are sitting down and saying, I'm going to just sit down and show everyone on the internet, because of technology like Twitch and YouTube. It enables people to go and actually teach this to the masses. And so if it wasn't for that, if it wasn't for Handmade Hero, I wouldn't have learned any of this stuff either. I'd still be doing like modern C++ and that sort of style of programming, and I'd have no idea what I was doing, because I had no one to teach me this stuff, right? I had no access to this sort of knowledge until, stuff like Handmade Hero came around. So if you're interested in programming and you found resources like this, then you're really in a wonderful spot, because you have such an amazing opportunity in front of you to actually learn from experienced people, and to see the appropriate way to do things, to use abstraction, right? To, how procedures should be used to actually have meaningful benefits to your code base and things of that nature. It's really a wonderful time to be alive in that regard, that this kind of information is, suddenly available to anyone and everyone. So that's my big rant for the day on abstraction and kind of how lucky it is we are to be programming when we are, where we are, in that we're able to see these things. We're able to go watch experienced programmers do this stuff and learn this stuff. That's a very amazing thing. It's certainly something that I'm thankful for and grateful for. Like I say, I wouldn't be, nearly as good of a programmer as I am right now if it weren't for those sorts of resources. And right now I study very heavily and very deeply. I do very intense study of Bitwise because that's very related to what I do. And it's just absolutely amazing the kind of, knowledge that you can gain from resources like Handmade Hero and Bitwise. So, it's a great time to be alive as a programmer. That's what I'd say about that. That's kind of the positive side of it, rather than just ranting about the way modern software is written. There's a good side of things. There's a kind of a ray of hope today. So that was a bit of a positive rant. You can think of a procedure like a spy who leaves with a secret plan, acquires resources, performs the task, covers his or her tracks, and then returns to the point of origin with the desired result. Nothing else should be perturbed once the mission is complete. Moreover, a spy operates on only a need-to-know basis, so the spy can't make assumptions about the spy master. Similarly, in the execution of a procedure, the program must follow these 6 steps. The first step is put parameters in a place where the procedure can access them. The second step is transfer control to the procedure. The third step is acquire the storage resources needed for the procedure. The fourth step is perform the desired task. The fifth step is put the result value in a place where the calling program can access it. And the sixth and final step is return control to the point of origin, since a procedure can be called from several points in a program. So this is a pretty important concept. So I'll take some time to write this out. And one thing I mention a lot on this series is calling conventions, because I've been saying again and again that in the examples they give in this book, it seems like they don't follow the correct calling conventions. This is kind of getting to that of what are calling conventions. If you've been following along so far, maybe you don't know what calling conventions are. And basically it has to do with these 6 steps. So let me write these out for you guys. So first of all, put params in place. And I'm just, kind of shorthanding it from what they wrote in the book. But transfer control. And that means transfer control to the procedure. The third one is acquire the storage resources. Next up, you have perform the task. Then you put the result in place. And then return control. Right. So this is what they're discussing, and I just want to go over this a little bit before we continue reading. Basically, calling conventions are all about this stuff here. Specifically, step 4 is just do the stuff, do the stuff that the procedure is supposed to do. But these steps here and these steps here are basically the calling conventions. You need to have some sort of convention of where does the procedure expect parameters to be? Like, where do you put them? And there needs to be a convention of, okay, I'm going to expect the parameters that were passed are going to be in these certain locations, right? And how do you acquire storage for resources? What are the specifics there? Where do you put the result so that the function that the procedure that called you, how does it know where to find the result? Where are you supposed to put it? How do you return control back to where you were called from? These sorts of things. These are, these all need to be handled by convention, because the machine doesn't dictate a convention for you. You can do whatever you want, right? It's just hardware. It'll let you do however, whatever you want, however you want to do it. But as a programmer, you ought to follow certain conventions, especially if you want to automate it, right? If you're just writing code in assembly, you don't strictly have to follow conventions, because you can tell the machine to do whatever you want it to do, right? But if you're writing something like a C program, it certainly needs to follow convention, because how else are you going to automate this stuff, right? This is why calling conventions are important. And so the calling conventions basically dictate sort of this step 1 and this step 5 in particular. You have 32 registers. One of them is the 0 register, but the other 31 registers, you kind of need to divvy those up. How are they going to be used, right? And so if you look at this green card that they provide you with this book here, you'll see they have the register name, use, and calling convention listed in a table here. And you'll see that, for example, x0 is the constant value 0, but then x1 is also known as RA, which is return address, right? So, look at step 6 here, return control. Well, if you're going to return control, see, basically, if you have a series of, instructions like add, load, double word, sub, jump, blah, 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 these have, each of these instructions lives in memory. There's some address where each of these instructions is living, right? And when you do a jump, or if you call a procedure, for example, which is just a jump basically, if you're going to be doing that, essentially what you do is you store the location that you're currently at, which is the program counter. I believe I've talked about the program counter before in previous episodes. One of these registers, or I guess actually it's not one of the, it's not one of the 32. It's actually like a special register that you can't directly access in RISC-V. But there's a program counter register that the machine has, and that tells you what address you're currently pointing to in terms of instructions. And essentially what you do is you just save that somewhere, and then you jump to whatever procedure it is you want to execute. So, you know, say I want to call foo, right? Well, this is going to jump me to some other sequences of instructions. You know, some kind of blah, 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 right? And, you know, this, you know, the start of this here is going to have some address where this sequence of code lives in memory, which is going to be different from, you know, this stuff. This is somewhere else in memory. And so when you're doing a call, you're jumping to the start of this code over here. But in order to do that, you're also going to save the location you're currently at to the program counter, or I mean, you're saving the program counter to a register, which you can see from the green card. The return address is X1. The X1 register is the return address, right? So what you do is essentially what you write is the current program counter, so whatever address you're on, plus 4, because, you know, 32-bit instruction, so plus 4. 4 bytes is 32-bit, right? But you don't necessarily, you know, if it's like compressed instructions or something, then it's not going to be plus 4. So you don't need to worry about the actual, how much further you're incrementing it by. But basically, you just store the location of the next instruction you're going to execute. So, you know, if you're doing a call, let's say the next instruction is an add, you know, you're going to store the location of this instruction. So what's going to happen is this location here, let's just, you know, pretend I have some address here. This is going to get, you know, put in the return address, and then once you're done with this sequence of code, this sequence of code is going to essentially take the return address and jump back to it. So once it's done, you know, it's going to jump back over here, and that's, you know, going to happen from a ret, which is a pseudo instruction for like a jump. Again, same with the call, is just a pseudo instruction. Right, the call is essentially just this line here of, you know, jumping to this and storing in the return address, and then the ret is just jumping back to here from, you know, the return address that you stored. This is a a bad diagram. I maybe made it more confusing than it needs to be, but you know, the concept is pretty simple. You're just storing where you were, jumping to somewhere else, doing some stuff, and then jumping back to where you were, right? And like I say, in order to do that, of course, you need to store where you were, right? You need to have that saved somewhere, and it's just a convention that, you know, you put that in a register, which is the register for holding the return address. And then you might think, well, what if you're gonna, you know, what if you want to call a procedure that calls a procedure? You know, isn't that going to overwrite the return address, right? And you know, you're exactly right, but they thought about this, of course. There's a convention for that too, right? So what you do is they have these conventions for callee saved versus caller saved registers, and temporary registers. And the whole concept there is that when you call a procedure, they have conventions about some registers. It's fair game for the the procedure that you're calling, it's fair game for it to use certain registers and not worry about it. And so when you're done with the call, the caller, the person, the part of the code that does the calling, it needs to assume after the call is complete that those temporary registers, whatever was in them before you did the call, you need to assume that that's gone, that it's garbage now, because the procedure that you called is allowed to use those registers for whatever it wants, right? So that's what a temporary register is, right? That's just a convention that says, it's convenient if when you call a procedure, that procedure has some registers that it's just allowed to do whatever it wants with, right? That's just a convenient thing. And so that's what a temporary register is. But then there's also saved registers. And the concept of a saved register is that when you call a procedure, you want to be able to have some stuff that after the procedure returns back to you, you still want the stuff that's in those saved registers to be there, right? It's useful to be able to say, I don't want the procedure I'm calling to overwrite these registers. I want to, know that my stuff is still going to be there after I've called a procedure. And there's two ways to do that, of course. You can either say that the caller needs to save them, which means the caller needs to put the value, the stuff in those registers somewhere. It needs to save them in memory. Then it calls the procedure, and then when the procedure returns, it needs to restore those values from memory back to the registers they were in. That's a caller saved register. And then there's callee saved registers, which is where you say the caller doesn't need to worry about it. You just call the procedure. And then if the callee wants to use those registers, it's responsible for saving the contents in memory. Then it can use the register. Then when it's done, before it returns back to you the call site, it needs to restore those values from memory back to the appropriate registers, right? So those are just two different possible conventions of how you go about saving the values of registers so that a procedure can be free to use those registers, right? There are by convention, there are certain registers that are caller saved, certain registers that are callee saved, certain registers that are temporary, and then of course there are certain registers that are for passing arguments, or the parameters, which is what this is talking about here. There are specific registers that are dedicated to doing that. They're basically just like temporary registers, but the idea is by convention you pass arguments to them, and so a certain register will be the first argument. The next register the next argument register will be the next argument to the procedure, and so on and so forth. It's a little bit more complicated than that because it depends on the type. Like if you have floating point values or integer values, or you're trying to pass like a structure, things like that. But that's the basic idea, right? And so that's how that works basically. And then again, for put the result in place, again, there's just a register that's dedicated to, by convention, it's where you put the result. And in practice, what it is it's just one of the argument registers gets reused for that. And again, I'm kind of simplifying a little bit because there's actually like multiple registers, because if you have a value that's bigger than your than a single register, and then what if you're like returning a whole structure, then you need to deal with memory, and so it's a little bit more complicated in practice than just a single register. But to simplify, I just want to, you know, point that out rather than what the book does, where they just give you a half truth. I'm going to say, you know, yeah, it is a little bit more complicated, but if you're just concerned about the base instruction set architecture, the integers, just the hardware for, you know, the instructions that operate on integers, then essentially you just need a single register for the return value, and one register for each argument. And so there's a fixed number of arguments, and then after that you need to spill over to memory. And yeah, that's basically how that works. And then, you know, transferring control, this step right here, essentially what you're doing there is you're just doing this, what I described, where you need to save the location of the next instruction in the return address register, and then you need to jump to the address where the procedure starts. That's what this transfer of control is about. And then, you know, when you have a procedure, basically the way it works under the hood is your procedure has kind of three parts to it. It has the and I don't know if I'm going to spell this right, prologue. That's definitely not spelled right. How do you spell prologue? Let me look it up. Prologue. So you have a prologue, you have the body of the procedure, which is where all the good stuff happens, the computation, and then you have the epilogue. I think it's epilogue with the. Let me just double check it since we're doing that. Yeah, epilogue, right? So a procedure is broken into these three parts, and the prologue is responsible for this bit right here of acquiring storage resources. The body is responsible for this step here, perform the task, and then the epilogue is responsible for putting the result in place and returning control. And it also, they didn't say it here in these 6 steps, but it also needs to, you know, do the reverse of this. It needs to clean up, basically. And so the way this works is basically what happens is, you know, your program, you have memory. Here, let me break out the fancy mouse mode. So you know, here's some memory. Right, and it goes on like that. Again, by convention, the stack grows down. So basically what we mean by that is you have high addresses over here, and you have lower addresses down here. And so when you have some memory, and basically the way this works is, well, you can look it up. The layout. So I'll look it up for x86 just because that's going to be easier to find than RISC-V, but let's see if we can find a reasonable diagram here. Yeah, so here's a somewhat reasonable depiction of how this works, right? I guess you can't really get it bigger, but so this is the idea here. When you have a process in memory, the way it lays it out is it actually has a very specific way in which it lays out the contents of memory for your process, and this is handled by the program loader from the operating system. And so for Linux, what it does is you have some memory, kind of the low end devoted to, or I guess the high end. Yeah, the high end devoted to kernel space here. And then after the kernel memory, it gives you the stack space, right? And so the stack starts at a high address and it grows down towards lower addresses. And then meanwhile, kind of somewhere in the middle, you have space where when you do like an mmap call to like if you want to map a file into memory, and you can also do anonymous mappings where you just get back some memory for your program to work with. A memory allocator might use mmap, and these sorts of things get allocated here, and that grows up towards higher addresses, so it grows towards the stack. And then below the space where the mmap stuff is happening, you have the normal program heap, which again grows up towards higher addresses. And then further, lower, you have the text section, which is where your actual code lives in your executable. The actual instructions is all in the text section, And so that's kind of how the layout of things works in memory. And it's, of course, it's... I don't know how much I want to get into this, but there's, virtual memory and paging that happens. It's not like physical memory addresses. These are, it's virtual memory addresses, and the operating system and some hardware is responsible for managing memory mapping between virtual addresses that a process has and actual physical pages. And so your process sees a big, a huge address space that's all of it is for the process. It sees this giant address space that it can use. But in actuality, it's just the stuff that's being used is getting mapped to actual physical pages. You don't actually have like a giant open address space of, like a giant contiguous space of free memory for you to use. It's actually that's what your process sees, but in actuality, the operating system and the memory management unit of the processor is doing some work to map between the virtual addresses that your program sees and physical pages when it actually needs, physical memory to back to back something. But so you have this stack here, and the stack is the bit of your memory space that's being used for this sort of stuff that we're talking about right now. which is why I bring this up. So this, what I've drawn here is just the stack, right? So this is your stack. And essentially what happens is when you are putting parameters in place, you know, if you run out of registers to use, or you have something that, you know, isn't gonna really be able to be used in one of the registers, basically just think of, if you run out of registers to use, well then where else are you going to put parameters for your program? Well, they're going to go in the stack, of course, right? That's where they go. And then, like I said, you know, when you're the caller and you're calling a function, if you need to save, you know, caller saved registers, you put them on the stack. If you're the procedure and you need to use callee saved registers, you save them on the stack, right? Those things go on the stack. When you acquire storage resources, what you're doing is you're grabbing some space on the stack, right? You know, you're grabbing some space here to put local variables, right? So when you have a program and you're using local variables in your procedure, those are actually at the start of the procedure. It's gonna make space on the stack for all of your variables, basically. Then it does the actual work of the computation, and when it's done, you know, it puts the result in the register that's used for the result of the procedure, and you know, it frees up all the stack space. You know, so when you allocated, you know, grabbed a bunch of space like this, but then when you're done, you free it again. You just send the stack pointer back up towards a higher address, right? And that's basically how that works. And then you jump back to wherever you need to jump. And like I say, the epilogue, if you had to save registers for whatever reason, if the callee needed to save registers, the epilogue is responsible for taking the values in the stack and putting them back in the appropriate registers before you do the return controls thing right here, right? And this is all kind of by convention. This is how we structure things. So I know my diagrams here are confusing and it's not like necessarily the best description, but to talk about this, we're kind of jumping into a whole bunch of platform specific details because it's all about, you know, the conventions of your whatever platform you're on. But you kind of need to talk about it because all of the whatever platform you're on, they're going to have some conventions for these things, and this is, you know, a typical example of how this stuff is done, right? So the details might vary between platform to platform. Different operating systems, you know, maybe structure the layout of a process differently. You know, your conventions for how you save registers and so on and so forth, that can vary between architectures and, you know, so on and so forth. This stuff is, you know, it's just, you know, you need to get introduced to these concepts because this is the stuff that's going on, right? And the details can vary, but the broad idea here is the same across everything, right? They all have some conventions in place to do these generic steps, right? And your procedures are always, you know, prologue, body, epilogue, and like I say, they're doing these 6 steps that the book is introducing you to. So this is stuff you need to kind of begin to get familiar with. You need to be aware of these things at this point. And again, I can show you some stuff. How do I want to do this? Let's head over to code.risky.tv. Oh, of course. My DNS is like super outdated. It's GitLab now. So I'll just go there directly. gitlab.com/riskybusiness. So on Risky Business, we did a hello world, and I believe the code that I have on here is still out of date. I don't think it's necessarily correct. But we got a hello world working on the series on the High Five Unleashed, so you can see that on the show. But if this will load for me here, I'd like to show you. Well, let's see if I have it locally. Maybe not. This must be on my laptop. So, maybe I won't be able to show you. Thanks for nothing, GitLab and internet. Well, I wonder if it will load. I wonder if this is just an issue with Pale Moon. Maybe it's not my internet. Yeah, okay. So if we go to Hula, if you look at like the assembly example here, and I should update this soon with the actual one that we did on the series that we ran and, you know, actually got working. I should update it with that soon. But for now, we'll just look at this. So what you'll see in these things is like, you see this line right here, where we're messing with the stack pointer. Again, the stack pointer is just one of those registers, and if you look at the calling conventions on the green card, specifically the stack pointer is register x2. So what we're doing is we're doing an AND immediate x2, x2, and then the immediate is -16 here. And what that's doing is we're aligning the stack pointer. So essentially what we're doing here is, and remember the stack grows downwards, and -16 is just shorthand for it's just, you know, if you remember from previous episodes, 2's complement, it's going to be a bunch of F's, right? And then essentially the low bits with -16, what you're going to have is just two, like two nibbles, or no, one nibble. So yeah, it would be one nibble is just zeroed out. So 4 bits are being zeroed out, and so that's going to make the address potentially lower than it already was, which means you're allocating space, right? You're moving the stack pointer down to point, you know, maybe previously the stack pointer was here pointing at this address, but now you're going to move it down a little bit, right, and point it somewhere else, right? And the reason you're doing that is because you're aligning to a 16-byte boundary, and when you do that particular instruction, the ANDing with -16, you're aligning the stack to a 16-byte boundary, and you do that for convention purposes and potentially performance implications. And it can matter, I think, for like addressing modes and stuff. But anyway, that's a convention that you do. You align the stack pointer. And so if you look here, like here's main, for example, and you can see what we're doing right off the bat is we're allocating some space. And this time, we're not anding. Notice that this was an and, right? Here we're adding -16, so that means we're just moving the stack down by a fixed 16, 16 bytes. We're just allocating 16 bytes of space on the stack. And then what we're doing here is we're storing the return address. So remember I talked about how if you're going to do a call inside a procedure, right? Well, this procedure already has the return address set up to return from whatever called main, which in our case is start, right? You can see start here, called main, and call is the pseudo instruction that puts the address for the next instruction in the RA register, in the return address register, and then it does the jump, right? That's what there's a instruction for that jump and link register, but that's what call is doing, right? So call is setting up this return address and jumping you to the start of main. Well, main is going to need to call other procedures, right? And that's going to overwrite the return address. So we know that main is by convention responsible. It's, the RA is a caller saved register by convention. So main, the caller of write in this example, needs to have the return address saved somewhere. So it puts it on the stack, right? And that's why you allocated space here. And again, by convention, just by convention, the minimum you allocate is 16 bytes. So the space for like four 32-bit integers. But yeah, we're just storing the return address onto the stack, and then like I say, that's your convention here, where you allocated space at the start of your procedure. You allocated space and you save some stuff you needed to save, and then you do your body of your procedure. And then at the end of your procedure, you see you have the epilogue. So this was the prologue, right? Here you have your epilogue, where you're and excuse me, you're loading from the stack. You're putting the value that we saved earlier back in the return address register. You're getting rid of that space you allocated. You're putting the result into the result register, which is A0, which is also an argument register, but it's used for the return value as well. So we put the return code, so we're returning 0 from main here, right? Because we're putting it into the A0 register. And then we're doing the ret, which returns to you where the return address tells you to go. So we loaded the value we saved for the return address, and then we do the ret, which sends you back to here, right? This is an example of, you can see how this stuff is actually structured, where you have your prologue, your body, your epilogue. And you can see we're doing the stuff we talked about in here, where we're, putting our parameters in place. I'll show you that too. So like this call, you see we're moving S0 into A1 we're moving S1 into A2. We're putting std out file no into A0, which is just, you know, a constant, right? But see, first argument to write, second argument to write, third argument to write, we're putting them in the correct place, right? What we're doing is we're putting the stuff we need into the appropriate place for calling write. So we're putting parameters in place, in the place they need to go. That was step one. Then we transfer control. So you see right here, we transfer control with the call write. That's a jump, as I said before. It saves the, you know, the location of the next instruction in the return address register, and it does the jump. So this transfers control. And then in the write, this isn't a good example because it, you know, it doesn't have a prologue and epilogue, because it's it doesn't need it. And that's a thing that you'll see too in practice, where you can have a kind of a naked procedure where you don't need a prologue and epilogue in some cases, and that can be nice for like performance. But in practice, you'd probably actually want to inline these rather than actually having these procedures. You'd probably want to just inline them instead of doing a call. But anyway. The point is, you know, you do a call and then, you know, let's talk about calling main, right? When you do that call, once you've transferred control, you acquire storage resources, and you saw that in the prologue here, we acquired storage resources, and then you perform the task, and again, you see that here, all this, you know, the meat of the procedure is doing whatever the procedure needs to do. And then after we've performed the task at hand, we put the result in place and return control. And again, you can see that here that, and the book didn't mention it in the steps, but we also undo, you know, undo step 3, acquire storage resources. We free up those storage resources, we put the result in place, and we transfer control back, right? And again, ret is a pseudo instruction for returning to wherever the return address tells you to go. It's jumping back. So yeah, we see all the kind of the big ideas here that they're talking about of how this stuff works in practice. It's, you know, this is how these things are done. It's you know, this isn't handled for you. If you get down to what the machine is actually doing, it all needs to be done by convention, right? And so there are actual instructions happening to orchestrate this sort of dance. And like I say, it's all done by convention. And so, you know, these are the steps that need to be done, and it's accomplished through following conventions that are put in place by standards, basically. That's the idea. So now that you have, you know, a bit of an idea of what we're talking about here, let's see what the book has to say about it. So we looked over the 6 steps. As mentioned above, registers are the fastest place to hold data in a computer, so we want to use them as much as possible. RISC-V software follows the following convention for procedure calling and allocating its 32 registers. Okay, so this is going to be interesting. They're actually going to tell us the calling convention that they think RISC-V follows. And my prediction is that they have the incorrect calling convention, that it's changed since this was published. So let's see what they say. This is going to be interesting. They say x10 through x17 are the 8 parameter registers in which to pass parameters or return values. x1 is one return address register to return to the point of origin. Let's compare that with the green card here. So the green card says x1 is indeed the return address, But as far as the arguments go, let's see here. x10 through x11 are function arguments / return values. x12 through x17 are the rest of the function arguments. So x10 through x17 are the function arguments according to the green card, and I believe the green card is up to date. And that's what they said in the book. So that leaves me wondering. So the book, we have confirmed at this point that the book is up to date with regards to calling conventions, at least compared to the green card, which I believe is up to date. The book seems to be up to date with regards to calling conventions. So that leaves me to ask, why did you use the incorrect calling conventions in your examples up to this point, right? Because you clearly used, I mean, maybe it's, I guess we haven't truly confirmed that yet, because usually it's stuff like saved registers are temporaries. Usually it's like temporary registers where they're using registers that are not temporary registers in terms of the calling conventions. They're pretty like random registers that they pick. And so they haven't told us what they think the temporary registers are yet. So maybe they are out of date, and it's just that they had the argument registers like back then. When they wrote this, the standard for where you put arguments is still the same as it was back then. Maybe that bit hasn't changed. So like I say, I guess we haven't confirmed that they are using an out-of-date convention, but I don't know. I'm just a little bit, I'm still suspicious of that, but I'm beginning to wonder again, because they got the argument registers right at least. So I don't know. Maybe we will find out as we continue reading here, but let's just continue reading. So in addition to allocating these registers, RISC-V assembly language includes an instruction just for the procedures. It branches to an address and simultaneously saves the address of the following instruction to the destination register RD. The jump and link instruction is written JAL X1 procedure address, and it says that jumps to procedure address and writes the return address to X1. And in the margins here it says jump and link instruction, an instruction that branches to an address and simultaneously saves the address of the following instruction in a register, usually X1 in RISC-V. And yeah, like I say, X1 is the return address register. So you use the jump and link instruction. When I write call in my code and in my examples, you know, when you see a call pseudo instruction, that's actually doing a jump and link, right? It's just a nicer way to write it. It makes it clearer that you're doing a procedure call. Same with ret, that you're returning from a procedure. It makes it more clear. It's, you know, maybe a little less verbose, but it is just a pseudo instruction for that sort of thing. You are just, you know, jumping and using something like a jump and link. And again, if you have the RISC-V reader book, you can see very conveniently it has a great reference of all the instructions and all the pseudo instructions and what the pseudo instructions are actually, you know, boiled down to, stuff like that. That's a great resource for this sort of thing. So I highly recommend that book. I always keep that near me when I'm doing that sort of thing. It's a great reference. And you see on the book club, when I do examples that involve assembly, I'm referencing that book all the time. So highly recommend that one. We need to get back to reading that on the book club too at some point. It's been on the back burner for a while, but yeah, it's a great book. Anyway, So, the link portion of the name means that an address or link is formed that points to the calling site to allow the procedure to return to the proper address. This link stored in register X1 is called the return address. The return address is needed because the same procedure could be called from several parts of the program. To support the return from a procedure, computers like RISC-V use an indirect jump, like the jump and link instruction, JALR, introduced above, to help with case statements. So they say JALR X0 and then 0x1, where 0 is the offset. So let me just write that out. JALR X0, and remember X0 is the 0 register. So that's just a 0, and then this is 0 for the offset, and then X1 holds the address, and again this is RA, right? So, and it's saying that this is, this is a ret, right? Because it's just jumping you to where the return address says to go, right? The jump and link register instruction branches to the address stored in register X1, which is just what we want. Thus, the calling program, or caller, puts the parameter values in X10 through X17 and uses JAL X1 X to branch to procedure X, sometimes named the callee. The callee then performs the calculations, places the results in the same parameter registers, and returns control to the caller using JALR X0, 0, X1, which is what I, just wrote over there. And let's actually look at what the RISC-V reader has to say about call and return. So okay, so call, it's a pseudo instruction. It says it writes the address of the next instruction, PC plus 8 to X RD, then sets the PC to symbol, expands to AUI PC RD offset high, then JALR RD offset low RD. If RD is omitted, X1 is implied. So yeah, it's a combination of an add upper immediate to PC and JALR, and we haven't covered AUI PC yet, but I'll just go over that quickly here from the RISC-V reader. So if we jump to the documentation for AUI PC, okay, AUI PC, it takes a destination register and an immediate, and it says add upper immediate to the program counter. And what it does is it doesn't add directly to the program counter. It's kind of a misleading name. It adds the upper bits of the immediate, the program counter, and it stores the result in the destination register that you give it. So it adds the sign extended 20-bit immediate, left shifted by 12 bits, to the PC and writes the result to the destination register. So the idea here is when you do a call, your call takes a destination register and a symbol, but you can omit the destination register, which just means use X1 for the destination register. So what you're doing is you're saying, take the high part of the address in the destination register, add it to the program counter, and you store that, or I should say, sorry, I mean, take the high bits of the address of the symbol that you pass it, and add that to the program counter, and put that in the return address register, and then do a jump and link where you jump to the return address, but you are offsetting it by the low bits of the symbol. So the reason you do this is because an immediate can only hold so many bits, right? And you want to be able to jump farther than that. So the AUIPC plus a JALR pair, that pair of instructions, enables you to jump farther than you could just using the jump and link, because like I say, the immediate in that instruction, like in the actual instruction encoding, like if you remember back to the episodes in the past, like the last episode or maybe the one before that or something, we saw instruction encodings, and we saw how there are maybe like 12-bit immediates, 20-bit immediates, stuff like that, you know? If you want a bigger immediate than that, then this gets around that limitation, basically, of the encoding, that there is, only so many bits in the instruction that can be used for an immediate. The idea is you split it up into a high part of an immediate and a low part, and so you offset the program counter by the high part, and you put that in a register, and then you jump based on that register offset by the remaining low bits, right? That enables you to jump the full length that you need to go. It's just kind of a hack to work around that limitation of the encoding. And then you can do, in a processor that's meant to be more high performance, you can do what's called macro op fusion, where you detect the pair of AUIPC and JALR, and basically you fuse that into like a single instruction, basically. So a more advanced processor can do things like that to make things higher performance. But yeah, that's how a call works, right? It's just a jump and link register, and if you need to jump farther than that would allow, you have the AUIPC instruction, which is, like I say, just basically a hack to let you jump farther. That's the deal there. And then for ret, it says ret is a pseudo instruction for return. It returns from a subroutine. It expands to JALR, X0, 0 as the offset, and then X1 as the register. So exactly what they said in computer organization and design. This is exactly correct. This is what a ret does. So that's nice to confirm that they got that right in the book. So yeah, this is how call and return work, basically. And when you're writing assembly code directly, of course you can use pseudo instructions like call and ret, which I showed you in my example of Hello World. You saw that I was using call and ret, but in actuality, those are just pseudo instructions for jump and link register, right? And the call can involve AUIPC as well. which is just a hack to let you jump farther. So you don't need to worry about that, right? It's conceptually, it's just a jump and link register to call, and then a jump and link register to return. But the return, you're not actually saving it to a register, because this is the 0 register, right? If you write to the 0 register, it's still 0. It's just the constant 0 always. So what you're saying is you're throwing away the result of the jump and link register. You're throwing away the address you would write to the register. Just throw that away, and then don't worry about an offset, right? You're just jumping back to wherever the destination register is telling you to go. So jump back to the return address. That's all that's saying, right? With a call, again, like I say, it's the same concept. It's just instead of x0 here, you put the return address. So you're writing into the return address, and then you put your offset here, and you put your register for where you're gonna jump to. So you use a combination of a register and an offset to specify where your procedure lives, basically. And you can put the high bits of the address into the register using AUIPC, and then you offset it by the low bits. That's the trick. So that's basically how all this stuff works. Let's continue reading here. Let's see. I don't remember why I read this paragraph, so I'm just going to reread it here just to be safe. The jump and link register instruction branches to the address stored in register x1, which is just what we want. Thus, the calling program, or caller, puts the parameter values in x10 through x17 and uses JAL x1x to branch to procedure x. Yeah, I already read this, but I'll just continue reading it anyway. Sometimes called the callee. The callee then performs the calculations, places the results in the same parameter registers, and returns control to the caller using JALR x0, 0, x1. Implicit in the stored program idea is the need to have a register to hold the address of the current instruction being executed. For historical reasons, this register is almost always called the program counter, abbreviated PC in the RISC-V architecture, although a more sensible name would have been instruction address register. The JAL instruction actually saves PC +4 in its designation register, usually x1, to link to the byte address of the following instruction to set up the procedure return. And here they're saying PC +4 because we're talking about 32 bits, and 4 bytes in 32 bits, so they're saying +4, and that's what I mentioned as well. In the book, it actually, in RISC-V Reader, I believe we just read, it said it goes by +8. And I'm not sure what it meant about +8. Let's just take a look one more time, because like I say, I think it said something about +8, which I don't know what it was talking about there. +4 makes sense because 32-bit instructions, right? That's the width of a normal RISC-V instruction, if we're not talking about like compressed instructions or other crazy extensions that you might add to RISC-V. Let's see. So yeah, it says PC +8. I don't know why it says PC +8. I don't know if that's a like a typo in the book in the RISC-V reader, because you'd think it should be +4. I don't know why it's saying +8 in here. Maybe we'll learn more about this later on as we continue reading both of these books. Maybe there's some nuance there that I'm missing. But yeah, you'd naively expect +4, and that's what computer organization and design is saying too, of +4 because 32-bit instruction words, right? So yeah, I don't know what to tell you about that, of why the RISC-V reader says +8 in its reference. I can't give you an answer to why right now, but COAD is saying +4, and that's what I would expect too. Right, that's the naive thing that you would expect, is that it would be +4, not +8 for 32-bit instructions. So yeah. I don't know, should we take a moment to look it up in the spec maybe? That might be a good thing to do to get that clarified for us. So we have the spec open here, right? So might as well. So it should specify the pseudo instructions. And you can see it talking about stuff like, you know, the standard software calling convention uses X1 as the return address register, right? So you can see this stuff in the actual spec as well. And, you know, if you look here, it says JAL stores the address of the instruction following the jump PC +4 into the destination register, which is what we were saying, what we were expecting, right? We were expecting PC +4. So I think it's just a mistake in the RISC-V reader. Hopefully they get that corrected in future editions. I'll just continue looking through here to see if we're not missing anything, but yeah, I think it's just a mistake in the RISC-V reader. You know, again, we see here, you know, PC +4. So yeah, I think that's all there is to say about that. I think it's just a mistake in the RISC-V reader. So yeah, when in doubt, check the spec, right? That's interesting that they had that mistake in the book. Here's a good table too, where you can see where they specify who the saver is. And you can see what I talk about when I reference the green card that is provided in the book. You know, this is the equivalent in the spec here, the equivalent table. You can see the register, the ABI name. So like X1 is the return address. You know, when I talk about the calling convention for temporaries, we're talking about like X5, X6, X7. You know, you can see there are more temporaries down here, 28 through 31, so on and so forth. this is what we're talking about. And you can see whether something is caller saved or callee saved. So you can see that the caller is responsible for saving the return address, and that's what you saw in my code of how in the hello world where main was putting the return address on the stack, right? It was saving it on the stack and then restoring it before it returned, because it itself was doing a call instruction which would overwrite RA. So because it's the caller of the write instruction, the main procedure is responsible to save the return address, right? That's the idea there. So you see caller and callee, and you see the API names for all these. You have the stack pointer at x2, the return address at x1. You have temporaries, you have saved registers. You see here are where the arguments go to your function, and you see these ones are also return values. The book said that you can use any of them to return values, but the standard convention here is just A0 and A1. The X10 and X11 are the two that you use for return values. But yeah, and then you can see that it's obviously a little bit more complicated than just this, because, for example, if you have floating point hardware, the F or D extensions to the RISC-V spec, then you have additional registers for floating point values, and they have their own convention. So when you're writing a C program, you mix, it doesn't matter what the type is in your procedure signature, right? You just put all of them, regardless of the type. You just type them all into your procedure's signature. But in the actual, when you actually compile that down, it does matter. Integers go in integer registers, floating point numbers go in, floating point registers. That kind of thing matters, and there are conventions for this sort of thing. Like you see, here's where you put floating point arguments and return values, and more floating point arguments, and so on and so forth. This, that's something to be aware of, that it's not as simple as just using the integer ones, unless you're just writing code that is purely integer based, right? If you're dealing with stuff like floating point, or if you have structures and things, then things get a little bit more complicated, right? But yeah, that's a nice table to be aware of. Let's get back to the book here. So yeah, it said PC plus 4, which is what you would expect and is the correct thing. It seems like the RISC-V reader had a mistake in it. Here's an elaboration. The jump and link instruction can also be used to perform an unconditional branch within a procedure by using X0 as the destination register. Since X0 is hardwired to 0, the effect is to discard the return address. And so they say JAL X0 label is unconditionally branched to the label. And yeah, that's how that's done. Unconditional branches, like the J, is just a pseudo instruction for a JAL. And I mentioned that previously on like the last episode. And again, if we open up the RISC-V reader here and look at its reference, so you have J, which is just an unconditional jump, and it says it expands to JAL X0 offset. And so JAL is the instruction that takes a destination register and an offset. And then you also have JALR, which takes a destination register, an offset, and a register RS1. So you're jumping and linking, but then you also have a register that's specifying where you're jumping to. which, like I said, with a call instruction, you're doing a combination of an AUIPC and a JALR, and the idea there is that you combine a register and an offset in order to be able to jump farther. So JALR lets you jump farther than if you just use JAL, because JAL, it's just encoding where you're jumping to in the actual instruction as an immediate, right? And that has, a limited amount of bits to it to be able to do that. Also, it is time for me to end the episode here. I've hit my time limit, so I'm gonna wrap it up here. We will continue working our way through 2.8 in the next episode. Thank you everyone who tuned in today, if anybody did, and thank you also to everyone who watches on the YouTube archive, which is available at risky.tv. You can also follow me on Twitter at HMN_risky to get updates about the series. Thank you also to everyone who supports me on Patreon. It really makes the series possible. And I don't believe I have any new shoutouts to give today. I'm not going to check right now. Well, I might as well check. Let's take a moment and see. But I'm pretty sure I don't. Yeah, no new shoutouts to give, but like I say, it's greatly appreciated. It makes the series possible. And if you would like to support the series, you can do so at patreon.risky.tv. Also, there's a somewhat of an announcement for this as well. Let's see here. Yeah, so for those of you who weren't interested in using Patreon, I provided a Gumroad as an alternative to Patreon. I usually don't mention it just because I don't, want to spend forever mentioning all these different things. But I had a Gumroad available for some time now, and nobody was really using it. There are numerous reasons why it's not really beneficial for me to keep using Gumroad. So I'm leaving the Gumroad platform. Now your only option to support me is through Patreon, or to do donations through like PayPal and that sort of thing. And if you want to support me and get early access to videos, and you want to get access to the software I make on this series, you're gonna need to go through Patreon now. You're not gonna have an alternative. And that's just because, it's not worthwhile for me to maintain an alternative. It just doesn't, it doesn't pay off right now. It's not a viable thing. So I apologize for that, but that's how life goes sometimes. So you'll either have to use Patreon or not support me, or if you really want to support me but you don't want to use Patreon, you can contact me and we can see if we can work something out. So I said, if you really want to support me outside of Patreon, consider sending me an email or a DM, and I will see what we can do to work something out, like set up like some kind of PayPal based subscription or something. But there are additional considerations to that. Like if you live in the European Union, it's a no-go because there is VAT. The tax regulations for that are a nightmare, and so there are limitations to that. But I am willing to to work with you if you really want to support me. We'll see what we can do. But yeah, for most people, it seems like everybody just uses Patreon anyway, so it seems like that's maybe the way to go for people. Just use Patreon. But yeah, like I say, thank you everyone who supports me, and you can do so at patreon.risky.tv. No longer Gumroad, just Patreon. So with that said, I will see you guys in the next episode, and stay risky, everyone.